Hello everyone and welcome. Thank you for joining us. This video series introduces our latest works and provide insights from Sony AI's researchers. I am Chen Chen, and today I and my colleague will present our paper, COALA, a practical and vision-centric federated learning platform, which is accepted to ICML 2024. I am a researcher at Sony AI, and my research mainly focuses on federated learning, vision foundation model, diffusion model, privacy and security in machine learning. And this is my colleague, Weiming Zhuang. Hello, Weiming.
Hi, this is Wei Ming. I'm also a research scientist in Sony AI, and my research mainly focuses on federated learning and vision foundation model. So today we are going to present this paper together.
Okay, so let's get started with our paper presentation. So first of all, I would like to introduce our team. Our team is called PPML, which is short for Privacy Preserving Machine Learning. Our team mainly focuses on federated learning, vision foundation model, and data synthesis research, and applying them to Sony products. This paper was done by all PPML members, and it is part of our federated learning research. Weiming Zhuang, Jingtao Li, and I are research scientists at PPML. Jian Xu is an intern at PPML, and he is a PhD student from Tsinghua University. Lingjuan Liu is the team leader of PPML. Next, I will leave the time to Weiming to present the details of our paper. Please go ahead, Weiming.
Yeah, thanks. So I'm going to introduce more details about this paper. So before we get started, let's try to understand more about what is federated learning and why do we need federated learning. So traditionally, we have two training methods called standalone training and centralized training. So standalone training here means that we just train a model on the data set of individual entities. But this method will not result in good performance of the model because each entity may not have enough data to train the model to have a good performance. And centralized training can solve this problem by gathering the data from multiple entities into a central server to train the model. But it would also have the privacy issues because the data are directly revealed to the server. And it will also result in huge communication cost because we need to transfer this large amount of data from these multiple entities to a central server. So that's why compared to standalone training and centralized training, there is federated learning, which is a privacy-preserving distributed training method. So a typical round of federated learning training contains 4 steps. So the server will first initialize the model in the server, and then it will send the model to each of the entity to do model training. So the second step is that each of the entity would use the data on would use their local data to do the model training. And after that, the third step is that these entities would upload the model parameters to the server. And the last step is that the server would aggregate these model parameters to generate a new global model. And at the start of next training round, the server will send the global model to each of the entity to continue the next round of training. So federated learning is the process of continuing this iterative process until the training is convergence. It can protect data privacy because the data never leave each of the entity, and only the model parameters are sent to the server, and it can quickly incorporate new data. So over these years of development of federated learning, there are many federated learning benchmarks and federated learning platforms to facilitate the development of federated learning. But what we see so far is that there is no federated learning platform that can support the latest development of federated learning in the computer vision domain in 3 aspects as we summarized. So we summarized them into task level, data level, and model level. So that's why we propose this new federated learning platform, COALA. So it is a practical and vision-centric federated learning platform focusing on 3 different aspects. So including task level, data level, and model level. And it can support a wide range of practical federated learning scenarios at these 3 levels. So next, I will go through each of the level in detail and compare with existing federated learning benchmarks and platforms. At the task level, COALA can support more than 15 computer vision tasks, which is the most comprehensive federated learning platform on vision domain. The majority of existing federated learning platforms and benchmarks that can normally support classification tasks, but we extend from classification to support object detection, segmentation, and more computer vision tasks. And what's more important is that we are the first platform to support training multiple tasks in federated learning. So multiple tasks here means that we can not only train image classification in the federated learning process, we can train image classification, object detection, and segmentation in one federated learning process. And moving on from task level to data level. In data level, we focus on 2 aspects: data annotations and data distribution. And we are the first platform that supports different degrees of data annotation availability, so including all data being labeled, which is supervised federated learning, and partial data being labeled, which is semi-supervised federated learning, and no data being labeled, which is unsupervised federated learning. So supervised federated learning is commonly supported by all different federated learning platforms, but we extend from that to support semi-supervised and unsupervised federated learning, which are rarely supported by existing platforms. And from the data distribution perspective, we support label shift, domain shift, and continual test time shift. So label shift and domain shift are common problems that exist in federated learning. So for label shift here means that in different federated learning clients, there will be the differences in the labels. So for example, let's take the scenario of deploying federated learning in real-world scenarios on the streets. So for some of the cameras on the street, they may capture more of the cars. And for some of the camera on the other street, they may capture more persons. So because these differences on the of the objects in different locations, that would result in a label shift in federated learning. The domain shift is the problem that when we deploy these cameras in different locations, that the environment and the lighting conditions of these cameras would be different in different locations, and the images captured by these cameras would be different. So that will result in the domain shift in federated learning. And continual and test time shift is also a very common problem, because when you deploy the camera in real-world scenarios, the scenes that we focus on will change from season to season, from day to night. So that's why we focus on different data distributions in federated learning. Last but not least, our COALA platform also supports model level with different characteristics. So we not only support single model training as the other benchmarks and federated learning platforms, we also support federated split learning and personalized models. So federated learning split learning is especially useful for resource-constrained devices when we cannot fit a single model into this device. We can use federated split learning to split the model into 2 parts and only put part of them into the device for federated learning training. And personalized models here means that instead of only getting one global model that perform well on each of the different federated learning clients, we can get personalized models that perform well on each of the federated learning client. And besides this, on the model level, we are one of the first. So this is especially important to support the latest foundation models in federated learning training. So in summary, that COALA is a practical and vision-centric federated learning platform that we can support a wide range of practical federated learning scenarios at task level, data level, and model level. Next, I would like to introduce the overview of federated learning platform. So this is the architecture. It starts from the platform user, that the user will first submit the task to a federated learning server, and then the server would handle the task and distribute the federated learning task to federated learning clients. And after rounds of training, and iterations between Federated Learning Server and Federated Learning Client. In the end, the server will output the trained model and evaluation metrics back to the platform users, and then the user can take the model and deploy it into actual scenarios. So one thing I would like to highlight in our Federated Learning platform is that our platform supports 3 degrees of customization, including configuration customization, component customization, and workflow customization. So in configuration customization, that the users of Federated Learning platform can just simply customize the configurations by changing some of the parameters in the configuration, like, for example, changing the data set or changing the training configurations, and then they can start a new set of Federated Learning training. Component customization here means that the users can customize implementations of Federated Learning Client or Federated Learning Server, so they can just overwrite the existing training method in Federated Learning Client by implementing a new customized client. And when in their customized client, they can implement their own training logic and their own testing logic. And the last one is workflow customization. So the users can even customize their workflow. So there is standard Federated Learning workflow. So last is about workflow customization. So users can even customize the workflow of Federated Learning process. So together with this Federated Learning platform, we also release a benchmark suite containing a list of datasets and practical Federated Learning scenario simulations with these computer vision tasks. So in summary, we propose a new Federated Learning platform called COALA, which is practical and vision-centric Federated Learning platform. We hope that our platform can facilitate more efficient Federated Learning research and development. And our platform is open sourced in this link, so it is the official GitHub of Sony Research, or you can scan the QR code to get access to our source code. Yeah, thank you.
So the last part is question and answering. After the publication of our paper, it had attracted significant attention from the community, and we have received a lot of valuable feedbacks. In this talk, we would like to address some of the most frequently asked questions. The first question is about the ease of use. How easy is it to get started using this platform?
So it's actually quite easy. We have packaged this Federated Learning source code into a Python package. So the users can just install this Python package very easily with pip install. And I can show a quick demo. So this is the source code I have downloaded into my local environment, and I have set up install all the requirement environments. And I have set up and installed all the required Python packages. So next, I would like to show to you how to run a simple Federated Learning experiment. So first, let's just take a quick look on all the files inside this open source platform. And today we are going to have a quick run on this FE-MNIST dataset. So this is actually an example. We provide many examples in this source code, and this is one of the examples of running FE-MNIST. So this is actually the definition of the configuration that we want to run the task called FE-MNIST. And we define a dataset and also some of the training configurations. So if we want to run it, we can just use Python and to run this FE-MNIST example. And after running this command, it will start training. So it will first start testing the initial randomly initialized model. And then, so this is the accuracy of the randomly initialized model, which is only 1%. And then it will start several rounds of training. And now it is training the first round, and it finished the first round, which is get an accuracy of 15. And then it now progresses to the next round, which is round 1. So for this process, we only set it to 5 rounds as a demo. So we'll wait for it to finish.
It seems that we can use just less than 10 lines of code to make everything run.
Yeah, it's actually very easy. So while we're waiting for it, we can take a look on this config. So actually, we just need 2 lines of code. The first line is conda initialize, COALA initialize config, and then it's COALA run. And if there is no config that is input into the init, and it will just use the default config. Of course, the users can customize the config here. So as long as they can set the parameters, which is the first configuration customization that we mentioned, that they can customize the configurations.
Oh, that's great.
Yeah, let's see how the training goes. Yep, the training has actually finished for 5 rounds of training. And at the end of the training, it would output the training accuracies from 1% to the end of 37%, because we didn't train long enough. If we train it for 100%, 100 rounds, I think we will get to 80 or 90% of the accuracy. And it will also output the losses and cumulative training time, and also the total training time.
Okay, that's great. It seems that quite easy for us to start with the platform. Let's go to the second question. So the second question is about the foundation model plans. Foundation models has been a major topic of discussion recently. So does this platform have any further plans related to foundation models?
Yeah, so as I showed just now, that we support the federated parameter efficient fine-tuning of foundation model. So that's actually only one of the methods to fine-tune foundation model in federated learning. And we have plans to further support like LoRa fine-tuning and support more fine-tuning of more foundation models. Like there are more and more latest foundation model, including vision foundation models like CLIP, and also large language foundation models. So we have plans to further support these models in our platform.
Okay, actually our code is open source, and we welcome all people from the community to contribute to our platform. And that's it for today, and we hope you enjoy our presentation. Thank you for joining us today, and see you in the next video.